Can everyone hear me? Great. So I'd like to just start by thanking Amit and the organisers of the conference for giving me the opportunity to come here to India. It's my first time, and I can say I'm really enjoying it, as much as I'm enjoying learning some new things at the workshop as well. So I'm from... Is it not on? Oops. Very much still ongoing. In fact, it's been ongoing for a little while, and as I was talking to Amit in the taxi this morning, I realized I probably put another name up on my slides. So some work was originally started by Neil Burrell, who's somewhere else. I forget where. And he's started off this work, and I'm taking it on, so I should probably have put his name there. So there's a long distance apology for that. So you still can't hear me? This is a little outline of what I want to talk about today. I'm just going to put one slide up about Lagrangian data and data assimilation in general. It's just going to be a short slide because I realize Chris is probably going to tell you a lot more about that a bit later on. I then want to go and talk about the point vortex model, which is the system that I want to look at in terms of using the gradient descent algorithm. And so I'll go through, again, Elaine showed that earlier, so maybe I don't need to spend too much time on that either. I'll then go through and explain a little bit about gradient descent and our methodology and what it is and how I've applied it in this point vortex system. And then I'll show you a couple of examples where I've used the method to assimilate trajectories of the vortex model, either using full observations of the system or partial observations, and then I'll just go through and summarize. So much of the data in ocean and atmospheric science is basically Lagrangian data, and what that means is it's observations which are a sequence of position measurements which follow a trajectory through the flow of the system. But that's quite difficult to assimilate into models because obviously models are based on fixed grids and they solve equations in a fixed coordinate basis, so it's quite difficult, or it can be quite difficult to assimilate Lagrangian data in that sense. So one of the things that we can do, the solution, is to actually augment the state space so that you're including the positions of the data into the model itself. And that's what we want to do in the point vortex model. So again, Elaine's spoken about this a little bit earlier. So essentially the idea is we want to assimilate some noisy observations of a passive tracer through a point vortex model, point vortex system. And we want to have some idea about the underlying dynamics of the system through assimilating the tracer trajectories. And it could look a little something like this. So these are supposed to be noisy observations as you move through. So the point vortex model is governed by some underlying dynamics. And so these are the equations for the vortices themselves. So a dynamical model, and it's basically based on the velocities, the fluid velocities of the individual vortices and summed over. So it's a superposition of those individual vortices and the interactions between them. Where n is the number of vortices, and this here is a parameter that can be changed. And then, so the tracer positions themselves are also governed by the dynamics here. And so that's the model that we want to generate to assimilate our data into. Yeah, I think again Elaine has said most of the stuff that I wanted to say on that. So the model we're interested in this case is for 2 vortices and 1 tracer. Basically what we want to do is assimilate the trajectories of a set of observations of tracer positions into a model given a set of initial conditions of initial states of the tracer positions and of the initial vortex positions as well. What we can also do, so we can either do full observations of the system, so you can either look at, just as a toy model example, looking at the tracer positions the full way through the simulation, or as well as the individual vortex positions through time. Or we can go to partial observations where you take, which is a more realistic situation, where you take the observations of the tracer positions over time, and after the first initial measurement of the vortex positions, then you lose that information and you only concentrate on the tracer. So what we essentially want to do is use our gradient descent method and then make a comparison with methods that have gone before, such as the extended Kalman filter and particle filter techniques. So again, this picture has been shown before also, and it's from Elaine's paper, which basically just shows the stream flow of the vortex model. So you can see the two vortices up above and below. And the different colors of trajectories are basically different initial conditions for the tracer particles, and showing how they move around the system of flow. And you can see, but by starting in different initial conditions, obviously you get different trajectories and different types of flow around the system. So again, just a brief overview of what's gone before. So this table is again from this paper, basically just showing for different sets of initial conditions of the tracer positions. The two vortex positions are fixed in space initially, and for different initial conditions of where we observe the tracers from the starting position. This is what different models, different methods of assimilation predict. And these percentages are just the failure rate, so the amount of times that a trajectory can't be found through assimilating data in the model. And as you can see, so in this case, for instance, there's quite a high failure rate. And this just happens to be around, if I go back, around the saddle point on this one here. So as the what do I call them? The fields of flow become quite close together, you get some nonlinear behavior, and it becomes really difficult to assimilate those trajectories in. So there's quite a high failure rate, and we want to see if we can overcome that using our method. So gradient descent assimilation. I guess first we're going to assume that x is the trajectory of a model of a series of states, and that's governed by an equation, this equation here. And then what we essentially have is a sequence of noisy observations of the tracer positions over time, and they're in a two-dimensional space. So for each of the vortex positions, you have an x-coordinate, a y-coordinate. And obviously they're noisy, so the noise on these happen to be IID distributed. So in a perfect model scenario, which is what we're dealing with here, F is known exactly, and so is the noise model. And so essentially what we want to do is use the observations, which is usually all we have, assimilate them into the model, and then try and find a trajectory which is consistent with the model dynamics and the observations that we have. So as I just said, the goal is to generate a trajectory that's consistent with the model dynamics and also consistent with the observations that we have. Again, so the gradient descent method is described in this paper here. So what we want to do first, we have observations, and what we need to do is start off with some kind of reference trajectory. So that we can then assimilate the data and find a trajectory of the model which is close to the true trajectory of the model. And so there's a question of how do we go about doing that, given that we've only got our observations. So for our sequence of observations over time, we have a set of n observations. Each of them have m dimensions, so our x and y coordinates. And what we want to do is actually define an extended state space, so n times n, which in the case of the two-point vortex model, you have two vortices with two coordinates, two xy positions, and one tracer which also has two coordinates. So you have 6 times n, the number of observations, dimensions in the model. And what we want to do is define a mismatch function and then minimize our we want to find a trajectory of the model based on the whole of that state space rather than any kind of sequential procedure. So to create an initial trajectory, what we do is we take the observations, which are noisy here, and we use our model to project forward one step in time and create us a new set of states. So you can see by doing that, you've taken each one of these observations and you've projected forwards once in time using the underlying model dynamics from the point vortex model. And you can see there's a difference between, obviously, what the observation really was and what a one-step ahead forecast is. And that's called a mismatch. And what we essentially want to do is minimize the mismatch between those two things so that we end up with a trajectory which is close to the true trajectory. So what we do is define a mismatch, or the cost function, for the algorithm. And that's given by this equation up here. It's basically the sum of all of the mismatches of these individual sequence of observations or sequence of states. So by summing over them, we gain a mismatch over the whole set or sequence of observations. And we try and minimize everything at once. So rather than try and minimize one thing at a time, we minimize the whole system at once. So you can see. Oh. I'll go back one. So this is what we start off with, observations and an initial guess at what the trajectory might be. And then as we go through the algorithm, we're trying to minimize the difference between those two things. And as we step through, you can see you get this something that starts to look like a trajectory of the model. But it's not actually a trajectory. It's close, but it's not quite. So the assimilation, the gradient descent, finds something which is close to the trajectory, but it's not a true trajectory of the model. And what we've done is essentially started off with the observations themselves. We've made a reference trajectory and we've minimized the mismatch function. What we've ended up with, we've basically thrown the observations away and we've ended up with this function or this trajectory here. So if we apply that to our model of the point vortex system, so again we have 2 vortices, 1 tracer, and what we start off with is a set of observations of the tracer positions. And I don't know if you can see here, and what I should have done is actually plot the vortex position as well, since in this case we're looking at the vortex positions and the observations over the whole time period. So you've got 2 vortices here, initially located. You've got a starting position here, initial condition, and then basically showing how the observations, how the tracer moves through the system. And then so the image on the right is what happens after the algorithm, after you've performed gradient descent. What you get is a smooth trajectory of the tracers, and you get a pretty circular looking set of vortex positions over time rotating around each other, which which is good. It's close to what it should be. Again, I should have plotted truth on there. But it's very close, but just not quite. So this shows individual tracer positions over the assimilation period. So for an individual observation at any one time, we start off, before we do the gradient descent procedure, you start off with a point that looks something like up here. The line's going this way and this way are the observations either side of that, so either one before or one after in the sequence. And as you go through the procedure of gradient descent, as you're minimizing the mismatch function, actually what happens is this point comes down here and ends up around here, again with the points at either side being shown on the line here. Again, what I should have done is, yes? Go back. So this one, so this is the observations that we start off with and the initial positions of the two vortices. And this is how the vortex positions move with time, basically. Yes, so yeah. So again, just in this case, where the observation happens to start off and after the gradient descent procedure, this is where the mismatch function ends up minimizing the tracer positions too. And again, this is just the last one in the sequence.
So the dot is the actual observation where the descent starts.
Yes.
And this is sort of the path in the gradient descent space for one of those points on the previous figure.
Yes, exactly.
So then the second one, so the approach isn't actually monotonic. It can go far. The one in the middle sort of looks like it's farther away for a while.
Sure. Yeah. So that's what happened when we had a full set of observations for the system, but that's not really very realistic. So what happens in the case when we have partial observations, and what I mean by that is we have some observations of the tracer throughout a sequence of time, and we take note of the initial position of the two vortices at t equals 0, and then we let go of storing, of saving the vortex position. So we only observe them at t equals 0, and then we don't observe them anymore. So in this case, what we do is use a two-stage assimilation process. And basically what we do is estimate, so we need to make an estimate basically of, we have a full state space of which we've got some observations but some missing components of that state space, and we need to fill it up with an initial guess so that we can then do the gradient descent procedure. And what we basically do is take the observations and take the initial positions of the vortices with some noise, and we resample and we make a 1-step ahead and a 2-step ahead and a 3-step ahead forecast using the model dynamics to get a first guess at what a possible set of positions for the vortices might be. And so we integrate the equations forward and populate the full set of possible states. We then apply the gradient descent procedure to search for a trajectory, and you get something close to a trajectory, but again, not a trajectory. And in the second step, we then start again from the observation. So once it's reached an almost trajectory of the model, you take the initial guesses for the vortex positions as a better guess, and you reinitialize the original observations of the tracer positions, and then you go through the procedure again to get something which hopefully works well. So this is just demonstrating that for one particular set of initial conditions. So again, we have observations starting from t equals 0, a set of noisy observations of where the tracer positions are moving to, and an initial guess. So we have two initial positions of the two vortices, and we make a guess of where they might be in the system over time by just resampling from the noise and making a projection forward. So we get a really rough guess. You can see it's not really very circular at all. So then we obviously apply the gradient descent algorithm to get something in which case the observations are smoothed out and they're looking more like a possible trajectory. And again, the vortex positions are also becoming circular, but they're not quite a good trajectory of the model yet. So then what we do is we take this trajectory from the first stage, we reinitialize the observations. So we put the original observations back in, and we do the process again. So remember I said before that you start with the observations, you make a guess, and then you throw the observations away. So we're going to take the observations one more time before throwing them away and going down the gradient descent procedure. So this is just the result that we get in the end. And again, I should have plotted the true trajectories of both the vortices and the tracers on here, and you would have seen that they're very close together. So as I mentioned before, there are some existing methods for Lagrangian assimilation that don't do so well when you're in regions like this, where the flow lines are very close together and you get some nonlinear behavior, and the traces are basically rotating really fast around those locations. And so we've shown actually, so the situation I've just shown you was for that particular case, so an initial starting position of, I forget, 1 minus 0.6, which relates to this here. So where other methods break down, ours actually does pretty well, and that's due to the fact that we're minimizing this whole extended state vector in one go. So obviously, as I said, this is kind of a work in progress, and so there's still a lot of things to do. Again, what we'd like to do is compare it with some of the existing approaches that are out there and make more comparisons. But that's...
Could you say a word about the first comment, namely, what does it mean if the simulated trajectory is outside?
Okay, so basically what it means is that using a particular simulation, whichever you choose, I think it's a extended Kalman filter, what you find is that the model can't find a trajectory that's close enough to a true trajectory of the system, so it fails. So, sorry? So it occurs around these regions here where the field lines become close together. Mm-hmm. And so you need nonlinear, exactly, you need nonlinear techniques to deal with it, which is why that method fails, but ours doesn't. So I realize I've gone really quite fast. I'm sorry. But basically, in summary, we've shown that our method works in principle in this system. It's been shown to work in other systems as well, which Lenny spoke about at the workshop earlier in the week, and I guess he'll speak more about tomorrow as well when he gives his talk. But really just to say that this work is still ongoing. We'd like to do more and make more comparisons with different techniques that are out there. And also that, so we've shown that our model can, our technique can work in the case of partial observations, And also it works in the case where you have an imperfect model rather than a perfect model situation. Again, Lenny's going to talk about that more tomorrow. But yeah, sorry for going fast. Thank you. Sure. So I mean, so we would do a large sample of tests for different parameters and window lengths and things.
The filter parameters, how do you tune?
Sorry?
How did you tune the filter parameters? P naught, Q and R.
That's not bad to ask her, because she didn't do that work. She did. She's done a very good research.
True, but she said, he gave fits to simulation.
Okay.
No, I'm just, if you're not, it doesn't matter, but what I'm just sort of cautioning is that people who use the filter should not jump to conclusions about the performance of the filter before knowing whether the model inadequacy is there or the statistical inadequacy is there or somewhere down the line, your procedures are not exact. You come to some conclusion, blame something, it may not be correct.